तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
We have so far seen how to model a combination circuits in the previous lecture, and in this lecture we will be seeing how to model a sequential circuits. The simplest of flip flop is a D flip flop. So, we will start with that one so as to grasp how the coding is. It is same as such. Further, we will have one active low input called the reset. When a reset is applied, the flip flop is cleared. That is to say, Q becomes 0 and negative of that N stands for negative, but it's actually you can regard it as a low. People designers use this as well as low, and this is I think more popular than that. And another thing that we have seen here is a clock input. It is you have already seen that it signifies a positive edge clock. And once again, this positive edge of clock and asynchronous reset active low, these are all the very popular thing among designers, especially in United States, and we adopt this throughout our course as such. And now it's very easy to code this. See, what we want is, first we will cover, we will reuse the same always block, but connotation is different here in this case, because this is a sequential circuit as such. We will use always once again at. This portion is common to combinational as well as sequential, but here makes the difference. Now within brackets the same inputs come into picture, but this time it is going to be a clock rather than the ordinary signal logic signals. So that makes the difference. See, for example, you want this at positive edge. So what we do is we use a reserved term in Verilog called pass edge. Note this. If you make a spelling mistake, naturally the tool will complain, right? So now what we do is always give a blank, one or more blanks. right, at least one is mandatory, otherwise it cannot distinguish, tool cannot distinguish between this and this, right, and do not put an underscore or any other symbol, just plain blank as such. And these things are vital because you will have lots of difficulties with the tools later on. So now next is either at positive edge clock, or once again this is not logical, just plain English statement, and I can fold it to any number of lines, there is no restriction as such. It is similar thing as we have already mentioned, it is similar to C writing, wherein you have lots of freedom, you can put one here, one there, and so on. So what we will just list the next input, that is reset underscore n. So we have covered all the inputs, so to say. Basically the inputs pertain only to the clock, and notice that D is not appearing here. So, this indicates a sequential circuit. So what makes the difference is, here you would have actually put D in the earlier case, which is combinational. Here what you had to put only list the edge transitions, namely the clocks, right, and reset is actually strictly speaking not a clock as such, but it has a very special meaning. And why this reset underscore n, why should we go for low is, this normally comes from if you make a big systems, it will be, this reset will be residing as a master reset on a control panel or a panel, and you need to reset from there, and that will be connected via a long cable in general. Suppose the cable snaps, it should be returned to a safe value. So what we do in the circuit is, where the reset push button ends in this PCB, you just put a pull up resistor. If it is this signal, just put a pull up resistor. This is, say, if it is +5 volt operation, just this is the thing. So when a cable snaps, it takes to a safe value as such. That is the reason why it is in industry especially, this is a very important signal, and has to be given due care. And so is the case with clock. Although negative edge clock also will work, somehow positive edge seems to be more popular, because that happens to be the first thing to arrive and compared to negative edge if it in such a clock, right. And next we will take up reset condition first, and in this case, suppose if reset appears, then we have to take some action. We have already seen here reset. I have forgotten one more thing. See, I have not put, I said positive edge, I have not mentioned edge here, so this is a wrong statement. So what we have to do is put a negative edge. Right. So in sequential realization, or a say flip flop or register, another name usually encountered is a register instead of a flip flop. Hereafter we may be referring register as such, which simply means either a D flip flop or any other flip flops. Fundamentally, when you see a synthesis tool and finally get the circuit out of it for the code that you have written, you will be seeing only D flip flop in most of the places. In fact, almost all the places D flip flop will be used. And now coming to this, we have already accounted for negative edge of reset, but we will now when we write for reset, how do we write? We use a new term called if statement. This is similar to again C, and if else you have used in C, and if you use if here, what you can do is just take this reset underscore n, and we are going to see whether it is high or low. So in this case it is an active low, so we have to check for 0 as such. Notice that after if there is no comma semicolon, this is a very important thing. See, after this condition is satisfied, then start executing this following statements. It may be one or more statements. If it is just one statement, you do not have to put a begin and end, otherwise you will have to put a begin and end, more than one statement. So now let us see how many statements, I do not know right now. So let us, as we go on, we will come back and put what is required. See, for example, now what we want, Q is to be reset, that is Q must go to 0, and q underscore n must go to 1. So, let us put that statement. So, in order to do this one, we have only to put q. Okay. I will just give a space because we do not know right at this stage, we need a begin or end. So, I will just put here in case we need, we will put that. So, q must be equal to 0, right. Here one statement is complete, therefore, a semicolon as in C, right. Then we can write the next output also. Here what we want is 1 to come there. So, we will just put 1. Because it is more than one statement, we put a begin, end. So, this completes the resetting of the flip flop whenever a power on reset occurs or a system is being reset through a manual switch as we have seen earlier. And so, after this what we had to do is we have forgotten one more thing here, that is begin, and we should not forget an end corresponding to that. So, it is a good practice to follow indentation. For example, you can put here begin, probably you can start somewhere here, and if slightly with try to avoid using the tabs. Good practice will be to use manual spaces, because editor to editor there will be a difference, and unfortunately you may have to migrate from one editor to another editor as we see different tools later on. So, it is a good practice, but otherwise do not worry much about it. You can, in fact, I am violating that by putting tabs. I hope you will avoid that. And now what remains to be done is only D input reflecting on the output Q. I will write it right here. See, what we want is Q. So, what this must be same as D input, and Q n must be inverse of this D. So, for inverse you can use either exclamation or this symbol tilde, which I have mentioned earlier also. And once again you need being a block as such, you need to put a begin and end, and the program is over provided you put one more end corresponding to this begin, and you just compare how many begins. It should be even numbers, so many begins, and that should be a matching end for that. So, you just put it, now I am putting as an indent offset like that. So, this completes flip flop. You would notice that it is almost one to one correspondence with what a flip flop does. See, first you do the resetting, only thing is you have to take the trouble of writing two statements here, and in fact you can avoid this also and take care in the some other logic which you are going to do later on based on this. So, you can even dispense with this, in which case begin and end can also be dispensed. Now, I would like to point one more thing. You have had a new symbol here. It is not less, you have to read this together. So, this is equal to this distinguishes assign statements and this. In assign you had used plain equal to, all combinational you use that, and here you have to use what is called a non-blocking statement. The earlier one is called blocking statement. So, and this is if you do not put this one, again the tool will complain. So, take care of this. I think with this I finish flip flop. We will go on to using this as a basic concept. We will now see more and more complex registers. In the first line, correct or as vertical line, and towards the end add one more statement else. Here what you see in the picture is two registers as such. One register output is called pixel out P, P stands for previous, and it is a valid signal. In microprocessors you would have encountered data and its corresponding data valid as such, and this is precisely what it is, and it is a valid signal, not the data itself. Here this is one of the designs I made for video scaling as such. We will not go into the details of the same, and this is just an extract of a portion of that. So, here this pixel, when it is valid, pixel information is the image information. So, and when it is valid is indicated here, and these are all basically the same signals what you have seen except for few differences. For example, you have used an asynchronous reset here and then a clock input. Once again it is positive logic we will confine our attention to, and then there is one more signal called hold, we will come to that, and set and reset are two new terms introduced in this. And what it does is, for example, this is just a register and we want to either set or reset. So, accordingly you have to make a condition. Let us say the condition is if A bar B C bar, I have just simplified, it actually comes from the actual requirement, field requirement as such. So, this is in between as I mentioned. So, it is A bar B C bar, if this is satisfied, then this will be naturally 1, and then only this flip flop will be set to 1, that is Q will go to 1, and similarly if Q is to go to 0, we have to assert reset pixel out as such, and for that the condition is ABC as depicted in this gate, and naturally A, B and C are inputs. And we have one more flip flop here that also has similar signals, for example reset and positive edge of clock, and just as we have this pixel out, we have a P, we have a pixel out here. Actually this is the signal that we want, and this is actually a signal pertains to a previous clock. So, for example, in a train of clocks that you have at a particular clock, this has become mature and it has written into this, and but that is not the point of time that we want to extract this information, because data which is coming through another path normally is delayed because it has to come through several complex process such as addition, multiplication, etc. So, naturally you have got to have some mechanism of delaying thing, and because the data is delayed, we have to still keep track, keep pace with it. We need to delay this pixel out valid, which happens one clock cycle prior to what we want. That is the reason why we have one more register here. So, this is actually to delay a register, and the output is pixel out valid, for which the codes are like this. For the first flip flop as such, we have set pixel output, and we have already seen that it must be A bar, B, C bar, and this you are already familiar, and 1 stands for it is just one number of bit, actual number of bits is what is signified here together with this apostrophe, and B stands for binary. That means what follows this number, that is this 0, that is in binary. Suppose you want to have it in decimal, what you need to do is just replace this by D, and once suppose you have some 8 bits in a particular case, you don't have to write 8 times zeros, just 1 0 is enough, it will take care. And suppose you want an octal representation, replace B by O, and you want to have hexadecimal, replace it by H, and so on. Any bit precision you can use the same thing, and note that 2 equals are there, that means logic. You could have straight away put A and B and C also, that also would serve the purpose here, and this is again put deliberately in order to explain the alternate way. It is not only alternate way, because when we are going through hundreds of or even thousands of statements, and we may not be in a position to go all the way back and find out what the bit precision of a particular signal is. So, it is always a good practice to indicate that. So, this is what it does here. And another important thing is, when you write a statement, it is a good practice to have good comments. What is obvious in the statement, do not state that, because that it is already stating what you want to. So, put it in plain English like language here. For example, even this may not be that plain as such, and elsewhere you may see more plain language. So, pre-compute, which is a condition for setting this, right. All detailed explanation can have. Suppose the explanation that you have offered is not adequate, you can use slash star and followed by another star slash as in C, and put any number of statements inside that. And we have also seen a reset pixel out here using assign statement here. We put, which is very much akin to what we have already seen here. Here the difference is a equal to 1, b equal to 1, c equal to 1, implying that it is ABC which we are ANDing together. And notice that in logical statement we need to put double AND as such, right. And of course in assign statement, even if you put just one AND, it still accepts, but as a normal practice you should use this, because in sequential circuits we can put the logic inside the always block. There if you do not violate this one and just put 1, it will complain, the tool will complain as. Now we have seen that in the flip flop we have covered an always at then positive edge of clock or negative edge of reset underscore n, and there is a begin once again, and very same statement occurs here also. If reset is 0, here you could have put just 0 alone, right. When you do not put any other thing, it implies that it is a decimal number, and that also is valid because it is single bit. And if this is condition is met, you make that register output 0, and that is clear register when system is reset. So as I mentioned, you can write a plain language like this, right, and do not repeat what is obvious here in this. Now if this condition is satisfied, you do this, otherwise what should you do? The otherwise condition is specified by else if in this case, and we have also seen another control here called hold. See, whenever you have a system, you may be processing at a very rapid pace. So, and there may be other systems, a host system receiving this data as such, and if this host is not as fast as your system, naturally the host will have to hold you for the time being. So, unless you have a hold pin there, it can't hold, and that is the provision made for that. So, if a hold is 1 when it is asserted, then what we have to do is just hold the previous value. The pixel out p valid is again the same here. So, that means we are writing back its own value. In other words, we are not disturbing the value. So, we have to say do something at every point of time. You can't say you can't remain without doing. So, you have to and retain the value if the system is in hold. Or you can even try just remove this statement as such and find out what the tool reports. So, next is if those two conditions are satisfied, we are yet to cover set and then reset, and that is what we are doing here. So, one more else if set pixel out which was a bar b c bar, if it is 1, and we need to set this pixel out p as 1, and if reset is asserted, and then we need to set it, reset it here, and that is what we have put the comments as. And if none of these are satisfied, then you just use only one else, because this indicates that it is the last in that category of else if. And in this case again preserve the same value as such. So, that is do not disturb the contents. And now you have seen that if else if and finally else structure. If you just count 1 2 3 here and 4 and 5, from my experience, if you exceed this 5, your speed of operation will get hit. For example, if you are aiming at 100 megahertz operation on an FPGA, let us say field program gate arrays. So, you only by experience you get this. So, do not try to add more than these statements. If you are still forced to add these statements, what you do is you combine this outside the always block and then restrict this once again to 4 or 5, right. Smaller the number, better it is, higher the speed of operation that you get. With this we have completed the first flip flop as such. It's this with all the signals accounted for, and this is the output we have, and this will be connected to the next in a pipeline, we can say, so to say, but the pipelining is not the aim here, which we will be covering later on. This is only to delay the signal, as we had mentioned earlier, so as to keep pace with another signal such as data, actual data itself, say pixel out, which is the data. And we will now see this flip flop implementation, which is very much similar to this. So once again we use always at positive edge of clock or negative edge of reset, and you notice that when you go through the course, you will get again and again very same structure all through, and that is the beauty of this structure. And especially when you want to redesign something or even start on a new design, what all you need to do is just save your earlier project's file and simply rename to suit the new design. So that way it helps. And second thing is, you are not bogged down by so many details, I mean so many signals. If you don't stick on to this, what I have observed over the years, number of designers putting so many hundreds of variables in one always block, and the result will be chaos, and you will get drowned in the myriads of the signals, and so avoid that one. So you can always put any number of always, and you can rest assured that each of these always blocks will be functioning concurrently. So there is no need for you to put all together and not make the system work, and that will be a frustrating experience, especially for a beginner, and therefore even for a beginner this is highly recommended as such. And here once again what we have seen is, when reset is asserted, this pixel out is the actual signal that we want. Earlier it was P, pixel out P, indicating that prior signal for this. This is the actual signal that we want, which we want a delayed signal, but the actual signal was already pre-computed in the earlier cycle. So now once again we reset, because when a reset is encountered, we have to reset, and that's what we have put here. And if hold is there, just hold on to the same value as such, and if not, we don't. You just notice that we have used only 3 statements as such: if else, and in this case the difference is final output is pixel out valid, and your whatever is the input, which happens to be the previous value here in the diagram that you have already seen, and that's this. That is this, and here notice that input is this P and output is without the P. So that is what we assign here. The present value is assigned with the previous value, and note that this will be valid only at the following clock edge, positive edge. So the previous positive edge of the clock, this would have been set, and that gets reflected only in the next clock, that is here, right. And earlier thing, whatever was, it keeps on just delaying the actual signal. And how do you distinguish between present clock or next clock? It is actually by the signal. See, this signal is derived from the previous signal, and the previous signal is set only in the previous clock, and this is going to be set now, which happens to be the previous status only in the present clock. Is that clear to you? I will draw a small waveform also. So let us say this first flip flop, we are going to as per the always block, we have whenever positive edge clock occurs, and whatever is this D1 value here, it will get into this Q1, and suppose you have cascaded here, and D2 receives this Q1, out comes the Q2. Let us say at this positive edge, for that matter both flip flops will act, whenever a positive edge clock occurs, both will act, keep on acting. So now to start with, let us say even before this, let us say this both were zeros, let us say, for time being. That is a reasonable thing because we started with the presumption that reset is applied always when the system is initialized, and now both being 0, now what is happening, suppose there are a train of clock pulses coming earlier. So when you see here, whenever clock strikes, whatever is there here, it will go through. For example, let us say this was also 0 to start with. We said ABC, and ABC is actually not the actual field inputs, it may be an intermediate outputs as such, which is fed back, maybe it is from a counter and so on. So all of them, the whole thing is synchronous as such. So wherever you have flip flops, it will be all of them will be reset. So it is proper for us to assume even ABC condition is also reset for time being, right? Whatever be the thing, say whatever be this input here at this clock, so also this flip flop, it will come over here. For example, let us say there was 0 here, and this 0 would come right at this point immediately after this. Actually, if you implement on the chip as such, there will be a gate delay, and only here the data will be effective, but for simplicity we will just take here. And at this edge, what you have here is this Q1 being valid, so D1 and hence Q1, and now this forms the input for this. So when this was already 0, so when the clock edge was encountered here, it was also sensed here. So but it had seen a 0, therefore it would have put a Q2 also 0 here. And notice that, and because it was Q1 is 0 and it is going to change state only little later, not here, right here, right? Are we clear? So this is, although we applied this here, it is going to change only after a delay, and that means to say although we put the output right here, it is not here, actually it is slightly with delay. Therefore at the when the clock struck, this is going to sense 0 of Q1, not 1, and it will be sensing 1 only in this clock. Are we clear? So this Q2 will go only in this, hence you have got a delay. So whatever is the first flip flop, that only is being fed here, and that will take effect only with the arrival of the next clock pulse, right? Although it is all synchronous circuit, you have to have system clock running all through, and we will see more when we see RTL coding. And okay, coming back to this, the completed waveforms for the deep flip flops cascaded is shown. I think the program is clear, self-explanatory right now, and before we go on to the next example, we will just see what these statements are. So what it means.
So you are saying the hardware is clear, but the program also it works sequentially. Is that what you are saying? The assignment statements, pixel out, valid,
Yes.
pixel out, valid.
Yes.
Next statement.
Yes.
Pixel out valid is pixel out pre-valid.
Yes.
So that means this will happen only after this is done.
Yeah, yes, it is precisely the same. Yes.
Because the hardware delay is happening.
Yes, it's yes, that's true. That is because the core of the statement is right this here. So you notice that the previous value is only assigned here at the present clock.
So unless the previous value changes,
Yes.
it will happen only after the clock.
Yeah, a delay of a clock.
That could have explained there itself.
Yes.
Because everybody knows this.
Yeah.
Fine.
Okay, with, before we wind up with this example, we will see what it implies. If you say if statement, what it puts is a mux in hardware as such, and all of them are all put mux. That means to say one mux output cascades with another mux and so on. That is the reason why I said you should restrict this one to say 4 or 5 based upon our experience, as well as that would ultimately decide what frequency of operation that you get, and that is an important thing which I had to keep in mind as a designer. We will go on to the next example. This is to realize a count up, and this is also based upon a filter, flip flop, say a register, and once again you have a reset here, which is same as previous reset, asynchronous reset, and then we have in addition to this, suppose you want to have this this counter is, let us say, an 8-bit counter, and 7 through 0, and this counter output is named CNT underscore reg. Reg means to tell you as a ready reckoner, it is to reveal that it is a register HS. Register means a flip flop, and this is the 8-bit flip flop as such. So that is what is implied here. And we want to reset this counter when the counter value has gone to a particular value, let us say 255. Then when a counter value is 255, there will be another comparison circuit here, and another signal will be produced here. We call it, let us say, reset counter, and apply it here in this block. And then once you say counter, you need to have another signal to start the count. So it is rather an enable of the count. That is what is implied here. Although it says advanced count, it is not a clock as such. The counter will be counting on the positive edge of the clock. Every time a positive edge of the clock is encountered, this will be counted, and this is the output what we have seen here. And we have one more condition here, ABC as the enable for the counter as such, and once again ABC are inputs. So we have seen that reset counter is when counter register is equal to 255. Once again we notice that two equal to's are used here, being a logical statement, and what it does is it does the comparison, and if the comparison is true, then 1 is output, and that 1 only is assigned to this reset count. Is that clear? It is not the 255 that is coming over to this. This is only a single bit. The result is single bit once again, which is assigned here, and the actual, it's all based on the counter value as such, and that's what we have written here as the comment. And another thing is, this is a line comment as such, if I have not mentioned earlier. And similar to reset count, we need to advance the count, that is enable the counting operation, and so we put another assign statement, and this time it is ABC, which we have already seen earlier. And another thing is, notice that all these things are combinational circuit as such, and this is appearing beyond this always block, which is for the counter. This is the sequential circuit as such, and prior to this one we need to do the incrementing of the counter. So whenever so long as this advance count is asserted, and at the positive edge of the clock, and in order to do this one, we can do the incrementing right within this always block, but a better thing would be to pre-compute it, so that you don't waste time when the clock strikes, you start computing. You pre-compute and be ready with it. When the clock strikes, you merely transfer the result. So that would be a good design approach, and that will once again speed up the operation of the system. And what we need to do is, we just put we have to increment counter register, that is the output of the counter which we have already seen, just increment by 1. There is no note that there is no need for 1 stroke B and so on. So it can be a plain decimal number as such, and so the incremental value is assigned as a next value for the counter. Only this is a pre-increment thing. Actually it increments beforehand, and the incremental value will be assigned or not assigned depend upon this inside the always block. And once again we see begin and final end in an always block, and at positive edge of clock or negative edge of reset end. These are all the standard thing. As I said, it will keep on recurring later on. And if reset is, this also you have already seen, only difference is this counter edge, which is an 8-bit, is reset to 0 value. You can even dispense with this 8 stroke D. If you put 0, that also will work, and it will be easier, but a good practice is to put this, so that you won't get a doubt whether it is 8-bit or 12-bit precision later on. So it's a good practice to have this, and this naturally initializes the system as such. So next what we need to do is, when the counter was 25, we have already seen here, when counter is 255, then reset, and that's what we are going to do here, right. So if it is 1, then reset the counter. This counter output is receives 0 signal here. Note that this is only number of bit precision that there in this number, and D stands for the decimal number as such. Here it's meaningless, you can put any other thing you want or just dispense with that. And you want to we have seen all one if, then else if, then one more else if, and else. Once again we see that it does not exceed 4 or 5, right, and if it exceeds we will see consider another example also later on with this exceeding that. So we need to advance if it is 1. So we have already pre-incremented earlier using the assign statement, and now the clock will come only after a delay, because clock strikes periodically at one particular point. At that point when it does, so whatever was the pre-incremented value will be merely pushed into this counter register. Another alternative way was to dispense with that assign statement there, and thereby remove one signal. We are unnecessarily introducing one signal, but at with the aim of increasing the speed of processing. So that's a good habit. And here we could have put the same counter reg plus 1 right here, that also will work, but what is happening, only when the clock strikes it starts computing, right. So with this, if this is not satisfied, we will go on to we will not disturb the contents of the counter register. So are we clear about the whole thing? Next we will consider how to realize a monoshot, and it is a non-triggerable monoshot as such, with a desired delay of let us say 256 clock cycles, and for this you need to reset set the value of 255. Always bear in mind the delay you get is 1 clock cycle more than what you set. And if you want longer delays, you can either cascade more number of counters or increase the bit precision of this counter, and you have ample choice on that score. And once again you have a synchronous reset, and when the counter, now this time I have put D, because we are going to, what all we have learnt, we are going to put together all this in a single program and then execute. So if you just give the same name, it will be overwritten. So I am deliberately putting a different name for that. So here D stands for that, and this is 8-bit, and that's a trigger applied here, and this is a non-retriggerable. That means to say, once you have triggered, the delay starts. Any amount of further triggering will not really have any effect. So that is the idea here, and that's naturally a clock, and let us see how to code it. So once again we have an assign statement for resetting, that's also a register as such. So here we have combined, earlier I said we should avoid else statements not to cross 5. So here probably it crossed by 1. So I have combined two similar statements right outside here, and notice that there was a reset inside, asynchronous reset when it is 0, and then counter value also does the same thing of resetting the counter itself. So why not combine both in a single statement, and this is the OR statement that is doing here. So this is a logical realization of, and each of them will return a 1 if the condition is satisfied. And for example, counter 2 is 255, then it returns a 1 or this will influence this reset signal as such. And this one we have noticed that input is trigger, and we want to sense the rising edge of the trigger as such. How do we sense? One way is to put always and positive edge clock, and there you can't have more number of clocks. Maybe any system you need to restrict it to say 2 or 3 clocks, and don't cross that number. And so what do we do if you have so many other signals which also need to be sensed at the rising edge, or for that matter falling edge? So then you can do, what you can do is you can have another signal which will store the previous value. So every time the clock strikes the current value, you can push it into the another flip flop and then store it and use that one in the next clock. So you will know what is available in the previous clock, that status here. So by ending this one, say for example previous value is 0 and present value is 1. So naturally you can sense that it has a rising edge as far as this signal is concerned. This, and this is once again pre-incrementing the register as such. And one more always block is there. In this case, what we do is we take a decision based upon that reset. Here it happens to be two blended together, that is system reset as well as the counter reaching 255, and that's this precisely the same. And here if it is 1, and as I said earlier, there seems to be some mistake here. Is there a mistake? Should have been 0? No. Let us cross check that. See, this one, when it is 0, here it is 0, but what it returns is 1, and similarly here also. So it is okay. So this must be 1 only. So if it is 1, then only initialize. What are the signals to be initialized? See, for example, this counter output itself. So counter is although it is a timer as such, mono short vibrator, and we have designed it as a counter as such, and this is reset here, and there is its output we have already seen as a delay out, and that is also reset, and there is one more signal that we said will have a previous status of the trigger, which is also a flip flop, that also needs to be reset right at the beginning, and this being a block, we have a begin and end. If now we have another else if statement. If let us say if first we sense the output, if it is 1, right, 1 is not at 1, I mean delay is not at 1, it will be 1 later on, but anyway we put this as the priority condition. If this happens, if it is 1, what we do is we need to increment the counter, because this implies the once the output has become 1, it means the counter has started running. So so long as it is running, that long we can keep on incrementing it, right, the counter, and we also should not forget to put this current trigger value as a previous value, so as to use it in the next clock when it strikes. This is a previous status of trigger registered here. We are remembering what is the trigger previous status by pushing it in the current value into the previous register. That's what we have put here. And now if this run delay, which was the actual sensing of the rising edge, and if that is 1, whenever this happens, this is going to happen only once in a way, and if it happens, and what should you do? Delay out must be set to 1, and we have seen that in always block all this equal to our non-blocking statements, that you should not forget. And once again here you should not forget to push this current value into the previous value here. Now if that is not satisfied, finally you have one more block. So the last else, if will have only else, no if here, and if this happens, what you need to do is don't disturb any of the contents. We have used 3 flip flops, say, or registers, that is counter D, delay out, and trigger. Each of them is 1 bit in size, with the exception of counter D, which is 8 bits as such. And one more thing I wish to say is, we have seen this delay out as 256 clock cycles as such. So that's what we have by having the equating it with 255. And why 256, we will see when we see the simulation, we will have an explanation for 1 extra cycle. So and we have said earlier that mux are put cascading each other, and we will see one more point before we wind up today's lecture, and that is what this implies is it is a priority encoder as such. See, we have if statement occurring very first. So if this is encountered, and if this condition is satisfied, then it will execute this, process this, and then quit the whole thing. It goes out of the always block, right? no other statements occurring later on will be entertained. And similarly, if this is not satisfied, only it will go to the next one, and this in turn, if it is satisfied, it will go to this and once again come out of the always block, having executed the first one, or it did not execute the first one, that is why it has come to this one, and having processed this, it quits this always block as such, and so is the case for every other thing. And so now this implies it is a priority encoder. So top priority is always put first with this one, because naturally it is the reset which is very important, and we had to take a decision not give priority to the advancing of the counter itself, and that is why this is a priority encoder. Wherever you have a priority encoder to be implemented, such as in bus arbitration in multiprocessor systems, etc., then you can use this portion, this way of coding as such. So far we have seen how to make, write Verilog code for a simple D flip-flop, and then go on with a little more complex complexity introduced by adding cascading 2 registers, and then we spoke of non-retrieval monoshot as such, and perhaps you can take as an exercise how to do a retriggerable mono. You can amend the code for the existing ones. So we will see, we will continue with the sequential circuits in our next lecture too. Thank you.